Alright, this is a tutorial on phase changes. We're going to look at how a substance, in this particular case water that is frozen at negative 30 degrees Celsius, changes temperature as we have a steady input of heat. So the graph that you see in front of you is one of the key visuals that we're going to use to not only understand the concepts but to also solve problems. Alright, so at first glance one might expect that if I have temperature on the y-axis and some internal energy change, that as the energy goes up and up and up, we'd expect greater and greater temperature. Alright, and that does happen to a certain extent, but we see on this graph that there are two plateaus at B and D. So we want to not only understand what's going on macroscopically, we also want to understand what's going on microscopically in terms of the definition of internal energy. Okay, so let's start here at some arbitrary time where our initial energy is 0. So like I said, we have a negative 30 degree Celsius chunk of ice. All right, so the A line here represents a solid phase. All right, we'll define solids later on, but we have a pretty good idea of what's happening. So we can see as the energy increases, we have a steady increase in temperature, as one would expect. Okay. However, and what we would calculate about the change in internal energy of the solid phase, the heat flowing in from whatever our source is, would be our standard MC, but we're going to have a solid specific heat, delta T. And the final temperature is necessarily going to be the freezing point or melting point of water, which would be 0 degrees. Okay, so we have a steady increase until it reaches the melting point, and of course that's where we're going to transition into the liquid phase. Before we say anything further, an important thing to read on the graph is the slope. Okay, so the slope, if we take it, is by definition just delta T all over the amount of energy, so we'll call it delta U, and we know that delta U is MC delta T, so that's really just 1 over the mass of the water multiplied by its specific heat at that phase. And again, the specific heat of a solid water is different than liquid water, and if you recognize this, mass times specific heat is 1 over heat capacity, so we'll call that big C. So you need to be aware that the slope is in essence an inverse of heat capacity, or the inverse of specific heat times mass. Right, so going back, now we have B. So notice that during the B part, there's no change in temperature whatsoever, but we still have a steady increase of energy. Okay, so we know this is melting, and if we were to reverse the arrows, we would call it freezing. And like I said, we have a continued increase in delta U, but no change in delta T. Okay, so we can ask, what's going on here? Why aren't we gaining temperature if we're increasing energy, internal energy? Well, we have to realize that internal energy has more than just the kinetic energy of the molecules. Okay, so we can infer that none of the internal energy is going into kinetic energy of the molecules. They're not jiggling any faster. Okay, so if there's no change in the average kinetic energy or the overall, we have no delta T. So where is it going into? Well, remember, internal energy is a sum of all the kinetic and potential energy. So there must be an increase in the potential energy of the particles. What exactly does that mean? Well, the intermolecular forces are what bind the individual water molecules together. Okay, so there is a bond there, so there's got to be an electric potential there. And as we heat it up, we're essentially stretching those bonds. Okay, in other words, the molecules are getting further apart, like stretching a rubber band. So getting further apart, all the energy is going into basically breaking those bonds. So until we break them all, then we have, well, not all of them, but we start breaking them, we're just going to get a stretching. So during that time, no temperature change, but there's definitely internal energy change. So there's more thermal energy at this point in the graph than there is this point. Okay? In fact, if this point is all solid and this point is all liquid, then somewhere between them it's going to be partially solid, partially liquid, and that's an important fact to remember when we do some of our problem solving. So we need an equation that relates to what happens to the amount of energy input. Okay, it's input via Q, Alright, so instead of an MC delta T, where there's no delta T here, we need an equivalent equation. So the equation for a melt or a phase change is equal to the amount of energy goes into the mass once again, and then we have a new term, and we're going to call this L sub F, where L sub F stands for latent, alright, that's the L, heat of fusion. Okay, fusion is a fancy way of saying freezing. In this case we're melting, but it's going to be the same number going either way. Alrighty, so an important number to remember, actually you won't have to remember, but that is pertinent to the ice water phase change, is the value for that latent heat. It's a number that's associated with that particular substance as it goes through a phase change. So the latent heat of fusion of water is a fairly large number. It's 3.33 times 10 to the 5th, right? So 330,000 joules per kilogram. So if you remember the specific heats, which was on the order of thousands to high hundreds, we see that it takes quite a bit of energy to melt, if you will, 1 kilogram of a substance, 330,000. Okay, so let's continue with our graph. So now we're in the full liquid phase. Now we're going to steadily increase once again. Okay, until we reach the boiling point. Okay, which can be seen in D right here. So this is from here, from the one dot to the other, it's all liquid, and then we start transitioning from liquid to gas. Okay, so another thing to note about the liquid phase, right, now the line is longer than this one, but we started arbitrarily at -30. If we would go all the way down to absolute zero, it would be a longer line, is the slope. So we already said that the slope represents the inverse of the specific heat, or the inverse of the heat capacity. So we see that there must be a different slope here. Okay, and so we can say that this specific heat of the liquid, since it has a lower slope than the solid, must have a higher value because, again, they are inversely related. Okay, then at D we have boiling occurs. Okay, again, no change in temperature, but an increase in the amount of heat. Okay, very similar to B. Note that D has a longer segment. We'll talk about that in a minute. And like melting, there is a constant associated with a substance as it boils. So in this particular case, the constant is the latent heat of vaporization. So all the energy during that phase change is going into M times LV. And for water, it's even higher, or for boiling, it's even higher than for melting. So this value is 22.6 times 10 to the 5th joules per kilogram. Okay, so it takes quite a bit of energy to completely boil a certain mass of water. In fact, it's about 8 times that of melting it. Okay, so I've already said it's bigger, but we can see that it's bigger from the graph, based again on the length of the segment. Okay, it takes a whole lot more energy than to boil than to melt, and this is for a given mass. So if you were not given the values for a particular substance, you could infer that from the length of the graph. Alright, the last phase, of course, is the gas phase. And again, we have an increase in temperature, MC delta T. If you look back at your graph, or at least on the paper in front of you, the line just keeps going. It does, if you will, have a, it doesn't go on forever. Eventually, so much energy is going into it that electrons are ionized from the gas, and now we have the plasma, which we've talked about before in reference to stars and fusion. Okay, just FYI, if we go way down in temperature, for certain substances, for below 1,000,000th degree Kelvin, a bizarre form of matter emerges. And maybe we'll show some demonstrations of that on YouTube, called a Bose-Einstein condensate. Some of you, no, I guess you didn't see that at the U of R. They do make them there. Okay, they are a very interesting form of matter that was just recently developed in the past 20 years. Like I said, ask me about it in class, we can talk. So let's do some example problems here.